వాయిస్ రావట్లేదు మ్యామ్.
ఇప్పుడమ్మా ఇక్కడ వేసుకుంటామా? ఇప్పుడు వినిపిస్తుంది కదా? ఓకే కదా? ఓకే, ఎస్. అమ్మా వినిపిస్తుందా మీకు పాప? హలో, హలో శ్రావణి.
వినిపిస్తుంది మ్యామ్.
యా
వస్తుంది
యా,
వాయిస్.
విల్ స్టార్ట్ అవర్ క్లాస్.
ఓకే మ్యామ్.
Yes. First of all, good morning to everyone. Here today we have third semester class. You are all third semester from third semester students, kada?
ఎస్ మ్యామ్.
Okay. So here we have some. I am Usha from Department of Physics, Dr. B.R. Ambedkar Open University. So, and again, I am sharing the screen here. Yeah. here we have a third semester thermodynamics. Now we are able to.
మేడం మీ మైక్ అన్మ్యూట్ చేయండి మ్యామ్ వీఆర్ నాట్ హియరబుల్.
ఇప్పుడు ఓకేనా?
యా ఎస్ మ్యామ్.
Yeah, thank you, Amma. Thank you. Okay.
ఓకే.
So total we have here ఒక్కసారి కదా అమ్మ స్క్రీన్ షేర్ అవుతుందా?
నో మేడం.
లేదు మ్యామ్, రావట్లేదు.
స్క్రీన్ రావట్లేదా? అమ్మ ఇప్పుడు ఒకసారి చూడండి కదా. అమ్మ స్క్రీన్ షేర్ అయింది కదా?
ఎస్ మ్యామ్, షేర్ అవుతుంది.
Okay, we will start now. So our third semester subject is what? Thermodynamics, right? So in this thermodynamics, we have um, 4 blocks. This is a block 1, law of thermodynamics 1. Block 2, law of thermodynamics 2. In block 3, law thermodynamics potential we discuss in that block. And fourth block is quantum theory of radiation. Okay. So here in block 1, we will discuss that law of thermodynamics. In that block, we have 4 units. Kinetic theory of gases, zeroth law and first law we will discuss in this block only. Reversible and irreversible also we will discuss, and Carnot engine also we will discuss in this block. So come to the point of block 2. Here we will discuss and we will learn about the second law of thermodynamics and thermodynamics temperature, entropy, change in entropy in reversible process. So in this block we have total 2 units. Second law of thermodynamics we will discuss here, and entropy, about entropy also. And this is the third block. Thermodynamics potentials we will discuss in this block, and also Maxwell equations of thermodynamics also, and applications of Maxwell thermodynamics equations in detail we will discuss in this block. So we have here total 2 units, thermodynamic potentials and Maxwell thermodynamic equations and applications. And here, last one is a fourth block. We have, in this block, we learn 4 units we have total. Law of temperature and low temperature about we discuss in this block. Applications of low temperature physics we will discuss. We have teleconference in the month of February. The date is the 28th. We will discuss this low temperature physics and applications of low temperature. We have teleconference. If you have time, you open that one. Okay. And here black body radiation, 2 types we have. Those 2 types we discuss in this block only. One is classical concepts and quantum concepts we'll discuss here. Before that, we have to introduce, first thing is what is thermodynamics? What is thermos? Anybody? Anybody have you have any idea about this thermo?
ఎస్ మ్యామ్.
Yeah.
హీట్ని సేవ్ చేసేదాన్ని కూడా థర్మాస్ హీట్ని గెయిన్
Heat.
చేస్తుంది.
Yeah,
తర్వాత
very good.
కోల్ డౌన్ కూడా అవే ప్రాసెస్, అంటే కూల్ డౌన్ చేసే
Heating
ప్రాసెస్.
and cooling, both
Yes,
are
ma'am.
we'll see in thermos, right?
Yes,
In
ma'am. Yes, ma'am.
general, our real life also we'll use, for example, anybody have any idea about this thermos? If we want the store our hot water, where we store in hot water and cool water also, ఎక్కడ స్టోర్ చేసుకుంటామమ్మా?
థర్మాస్ బాటిల్ ఉంటుంది మ్యామ్, దాంట్లో స్టోర్ చేస్తాం.
Yeah, flask for tea.
Flask.
We have
Yes,
an
ma'am.
idea about that, no?
Yes, yes,
Before
ma'am.
that, we have to discuss about, first we know that what is thermodynamics, right? The thermodynamics is the science of energy. Conversion involves heat and other forms of energy. Here, anybody have an idea of energy? What is that energy? Shakti ante enti?
హోల్డింగ్ సంథింగ్.
యా, ఇప్పుడు మనకు మన శక్తి మనకు ఉంటుంది, రైట్? థర్మాస్ శక్తి థర్మాస్కు ఉంటుంది కదా, ఓకేనా? యా, లైక్ దట్ ఈస్ ఓన్లీ అవర్ ఎగ్జాంపుల్. హియర్ we are taking most notable mechanic work it will do, and it studies microscopic variables also. For example, for that microscopic, temperature, volume and pressure. Okay, here a thermodynamic system is a physical system, is defined as a microscopic region of the universe that is studied in this. For example, we have so many systems here. One is isolated system and closed system and open system. What will happen? This is a little bit of an introduction class about the thermodynamic system. So, for example, isolated system where we are using. For example, for that, what is the isolated system? For example, anybody tells you have on the screen here. One container we are using, right? So this is isolated system. This isolated system surroundings what we have here, environment is here. So in this isolated system, no exchange of matter or energy in this isolated system. Okay, what is here isolated system ante? Isolated systems are completely isolated from their environment. They do not exchange heat, work or any matter with their environment. అంటే ఇప్పుడు మనం ఏం చేస్తున్నాము, మనం గదిలో ఉన్నాం, గదిలో మనం ఉన్నప్పుడు ఒక బాక్స్లో ఒక ఎగ్ పెట్టాము అనుకోండి, ఆ ఎగ్ అనేది ఆ బాక్స్ వరకే సరౌండింగ్స్ లో ఉంటుంది, రైట్? ఇస్ ఇట్ కరెక్ట్?
Yes, ma'am.
యా, కమ్యూనికేషన్ సిస్టమ్ ఉండనియండి, మీకు ఏదైనా అర్థం కాకపోతే యూ క్యాన్, ఓకే, యూ
Okay,
క్యాన్ టెల్ మీ. ఓకే, ఆర్ యూ అండర్స్టూడ్ నో? సో
Yes, ma'am.
isolated means we are taking one box. In that box we are using one egg. What
Okay.
will happen here? That egg will not share the heat, work and any matter, right? This is one example for isolated system. So an example of this isolated system is a completely insulated rigid containers, such as completely insulated gas cylinder also. Okay, and another system also we have here, closed system. Here in this closed system, energy exchange may be occur. What is here occur means what? Occur means what? అవసరం ఉన్నంత వరకు. ఓకే, రైటా? యా,
Yes, ma'am. Heat ఎంత అవసరం
దానికి ఎంత అవసరమో అంత తీసుకుంటుంది. మనకి ఎంత అవసరం అయితే తింటామో మనము అంతనే తీసుకుంటాం. సేమ్ హియర్ ఆల్సో దిస్ క్లోజ్ సిస్టమ్ ఆల్సో వర్కింగ్ లైక్ దట్ ఓన్లీ. ఓకే, హియర్ ఇన్ దిస్ క్లోజ్ సిస్టమ్ వాట్ ఇట్ ఈస్ ఎక్స్చేంజ్ ఎనర్జీ, able to exchange energy, heat and work, but not a matter with their environment. Okay, for example, for this greenhouse we are taking here, and here one more system is there, open system. So here open system, everything will happen. Okay, energy exchange and matter also exchange maybe occur. Yeah, here for this we are using energy as well as matter with their environment. A boundary allowing matter exchange is called the, what is this? The matter will exchange is called the permeable. Okay, the, for example, the ocean would be an example for this open system. What will happen in ocean, amma? మనం ocean లోకి వెళ్తాం. Okay, ocean means what? Ocean means what?
waves
Anybody have an idea? Yeah.
ఎనర్జీ అంటే ఇప్పుడు వేవ్స్ ఎలా అయితే వచ్చిపోతుంటుందో ఎనర్జీ లేదా దానికి సంబంధించిన హీట్ కానీ ఏదైనా సరే కూడా ఓపెన్ సిస్టమ్ లో రెండు ఉంటాయి.
యా, ఇట్ విల్ హ్యాపెన్ ఎనీథింగ్ కదా, ఎందుకంటే ఓపెన్ సిస్టమ్ కాబట్టి ఇది. ఓకే,
ఎస్ మ్యామ్.
యా, అండ్ హియర్ హౌ ద సిస్టమ్ వర్క్స్ ఇన్ ద మ్యాటర్ ఆర్ వర్క్ వేర్ ఎవర్ ఇస్ దట్. ఓకే, when work is done, for example, when work is done by a thermodynamic system, anything, we have so many systems are here, no, isolated system అయినా అవ్వచ్చు, క్లోజ్డ్ సిస్టమ్ అయినా అవ్వచ్చు, ఓపెన్ సిస్టంలో అయినా అవ్వచ్చు. ఏదైనా ఒక వర్క్ జరిగినప్పుడు థర్మోడైనమిక్ సిస్టంలో ఏ సిస్టంలో అయినా ఒక వర్క్, ఇట్ ఈస్ యూజువలీ ఏ గ్యాస్ దట్ ఈస్ డూయింగ్, వీఆర్ యూజింగ్ హియర్ గ్యాస్. ఓకే, the work done by the gas is constant pressure. For that we have here, are you understood about this figure? What is happening here when work system, when we will use in work
constant
system?
ma'am.
Yeah,
Constant.
in first figure we are understanding that this is in constant. Okay, it is not moving from A to B. Okay, in second figure what you are understanding, it is little bit of moving from down. Okay, A to B. Okay, means here the work, when work is done, it is what happened here, this is nothing but a open system. Okay, and again come to here, how heat will transfer. Okay, we have in third semester one experiment is here, that is the lease experiment. There we calculate that conductivity of a bad conductor. What is this here bad conductor means? This is one example for how to heat is transfer from one place to another place. In Lee's experiment, we will take a T1 and T2, both temperatures. Okay. Here we will go to steady temperature. We calculate, we will take that steady temperatures of both. Okay. We have one is a disk, least disk we use there, and another one is a store of vapor. Okay. So here what will happen? In between that two boxes, in between we are taking that bad conductor. For example, for paper and glass. From the glass, the temperature will transfer from one place to another place in between both boxes, in between the glass. Suppose when we will take that glass. అవుతుందా? ఇప్పుడు రెండు బాక్సుల మధ్యలో ఒక గ్లాస్ బ్యాడ్ కండక్టర్ అనుకుందాం. అది దాని థర్మల్ కండక్టివిటీ వీఆర్ క్యాలిక్యులేటింగ్ దేర్. ఓకే. ఆ గ్లాస్ నుంచి పైన ఉన్న బాక్స్ లో నుంచి కింద ఉన్న బాక్స్ కి హీట్ ట్రాన్స్ఫర్ అవుతుందా కాదా?
లైట్ గా అవుతుంది మ్యామ్. అంటే ఒకవేళ క్లోజ్డ్ కండక్టర్ అవుతేనేమో ట్రాన్స్ఫర్ అవ్వదు మ్యామ్. ఒకవేళ నార్మల్ గ్లాస్ లాంటిది తీసుకుంటే మాత్రం హీట్ కింద దానికి కూడా ట్రాన్స్ఫర్ అవుతుంది.
వస్తుంది, కానీ లిటిల్ బిట్ వస్తుంది కదా.
అంతే అంతే మ్యామ్. మరి
low temperature will transfer from upper to down disk. Okay. When we are removing that bad conductor, what will happen?
హీట్ డైరెక్ట్ గా ట్రాన్స్ఫర్
ఆ
అవుతుంది.
బ్యాడ్ కండక్టర్ తీసేసాం, అప్పుడు ఏం జరుగుతుంది? వాట్ విల్ హ్యాపెన్ దేర్? ఫ్రమ్ అప్పర్ టు డౌన్వర్డ్స్ దట్ హీట్ విల్ ట్రాన్స్ఫర్. ఓకే. దెన్ వాట్ విల్ హ్యాపెన్?
Faster. It will transfer smoothly.
Very good. So from down disk, least disk, then again also we are taking there one thermometer. Again it will little bit increase the temperature. Okay. With that, time versus temperature, when we will calculate in that experiment, we'll calculate that what is the bad conductor thermal conductivity. Okay. Here that is one example we are taking how the heat will transfer. Heat is energy transfers from one body to thermal another body we will take here due to thermal contact when the system are at different temperatures. Now only I told you that when the temperature will transfer from one place to another place, that transformation we will see. Where we will see this temperature? In thermometer only, right?
Yes,
so,
ma'am.
Little. And here what heat conduction? That heat conduction is heat transfer by means of molecular excitation within a material without any motion of the material as a whole. For example, here heat transfers between, this is only we are taking the Lee's experiment is one example for this heat transformation. Okay. Then in radiation also, you know, anybody have any idea about the radiation in our real lives? Anybody have an idea about this radiation? Where we'll go for radiation? We will not go. For example, మనకి ఏదైనా అవసరం ఉన్నప్పుడు మనము ఆ రేడియేషన్ గురించి వెళ్తాం. ఏమన్నా ఐడియా ఉందా ఆ రేడియేషన్ అంటే ఏంటి?
Yes, ma'am.
Radiation means heat going to outerward from the body.
Very good. Yeah. Example,
this electromagnetic radiation, electromagnetic waves, and
very good. And again,
another
waves. Anybody, anything equipment we have that radiation? I'm asking that. X-rays.
X-rays and
very good. We are using in our
phones.
real life, we are using that microwaves.
Yes, ma'am. Microwaves also.
Radiation will not come?
Yes, ma'am.
From the microwaves?
Yes, ma'am. Radiations will be coming from the microwaves also, ma'am.
Yes, very good. X-rays, gamma rays, manaku MRI, these all we will calculate the radiation. That's why healthy person will not enter in. So here also, how in that radiation means radiation is heat transfer by the emission of electromagnetic wave, which carry energy away from the emitting object. For this object, have any idea of this object? X-rays only, right? For ordinary temperatures less than red hot, where the red hot we will see in the radiation part, infrared regions. We have so many colors in that. That way we are taking that. What is that? Wave numbers and infrared regions we'll use in electromagnetic spectrum. We have in electromagnetic spectroscopy will explain about this electromagnetic spectrum. Okay, the relationship governing radiation from hot object is the Stephen Boltzmann constant. Here we have Stephen Boltzmann constant. Boltzmann constant, anybody have number is class about this Boltzmann constant. Here we will calculate in radiation when heat transfers. P is equal to E sigma S T power 4 and R minus T power 4 suffix X. Here P is the power of radiation. Okay, we are using here. Heat is Q. In the place of we are taking sigma, and it transfers in the unit time, that is T. We are explaining what is E and what is lambda and what is sigma, sorry, and what is S. What is this S we are taking? S is the radiating area. For radiating area, surrounding of that area, where is the radiation will coming outside. Okay. So this is a TR absolute temperature of radiator, TS absolute temperature of surrounding, E is the emittivity from radiator. In black body we will use that. Okay, here this is introduction class. You think that what is entropy? Anybody have entropy idea? Entropy.
Yes, ma'am. Heat reducing, we can say, ma'am.
Yes, heat. Here we will see the proper definitions of entropy. Entropy is a state variable whose change is defined for a reversible process at T, where Q is the heat absorbed. Here, that is the low entropy and high entropy, and which came first. Okay. Here also Q by T. What is the here Q?
Quantity
Q
of
is the
heat.
heat absorption. Okay. And what is T?
Time. Temperature.
Temperature. We are using temperature in thermodynamics. Okay. Okay. Next. And again, also we have another definition. Also we have here entropy, a measure of the amount of energy which is unable to do work. So is a measure of the disorder of a system. We discussed about that different types of systems like that closed system, isolated system, and what is that?
Open system.
Open source.
Yeah,
Open
open
system.
system also we have that. Okay. And also this entropy is a measure of the multiplicity of the systems. Any system we will use this entropy. Okay. Low temperature, and where we will use this low temperature and high temperature, we'll take that. Okay. And in this entropy in terms of heat and temperature, how we'll take this? A change in the entropy can be described as the heat added per unit temperature. We'll use this equation part, already we take. Q is the heat flowing into or out of the system. Both out of the system, internal of the system also we will use this Q when we will use this equation part. So this is often sufficient Definition of entropy. Entropy, if you don't need to know about the microscopic details. What you are understanding about this word? Anybody? What you are understanding about this word? This is often a sufficient entropy if you don't need to know about the microscopic details. What you are thinking about this word? Don't need to know about the microscopic details. Okay, let us move. Yeah. Tell me.
నార్మల్గా మైక్రోసాఫ్ట్ దాంతో కాకుండా మనం ఇంకా దేనితోటి ఎంట్రోపీని చూసుకోవచ్చు అనేసి.
ఎస్, ఓకే. ఇన్ డీటెయిల్ గా కావాలి అని అంటే కదా. యా, ఇట్ కెన్ బి ఇంటిగ్రేటెడ్ టు క్యాలిక్యులేట్ ద చేంజ్ ఇన్ ఎంట్రోపీ డ్యూరింగ్ ఎ పార్ట్ ఆఫ్ అన్ ఇంజిన్ సైకిల్. ఇప్పుడు మనకు కార్నాట్ ఇంజన్ ఉంది. కార్నాట్ ఇంజన్ లో మనకి ఏమవుతుంది? ఇఫ్ సపోజ్ కార్నాట్ ఇంజన్ we have in our book Carnot engine. You know about the Carnot efficiency of heat engine?
We don't know. We have not.
Their reversible process in 4th unit. If you have a textbook with you, anybody open that textbook that is in 4th unit.
Carnot's engine. Okay. 46 page number.
What will happen in this Carnot cycle?
Carnot cycle.
Yeah. Carnot engine, that is a 4th unit we have there in our text. If you have textbooks with you.
Yes, ma'am. It can be reversible or irreversible.
Yes, reversibility of Carnot cycle. What will happen? What will happen is there?
In two temperatures, we can. Just now we have discussed, ma'am, two temperatures measurement.
Okay. And here also heat engines, we are speaking about that heat engines kada. So there we use the eta is equal to W by Q1, page number 50. If you have, you open that. Efficiency of heat engine we will calculate with this eta is equal to W by Q1 is equal to Q1 minus Q2 by Q1, right? That is equal to 1 minus Q2 by Q1. Yeah.
That Q1 is source, Q2 is sink.
Yes, very good, Amma. So like this we'll calculate efficiency of heat engine. Here we will come again in this part. This is the concept of entropy. When we'll study the concept of entropy, gives us a more quantity way to describe the tendency of energy to flow into the particular direction. About this direction also we have in figure 4.2 in our textbook. Carnot cycle. In direction where it will move. From A to B it will move, and B to C and C to D. We have here the
A
graph
to B,
also. Yeah.
Yes, ma'am. A to B is isolated.
Yeah, very good, Amma.
B to C is adiabatic.
Yeah, adiabatic system. Very good.
Yes.
C to D is
C to D is also isolated, ma'am. D to A is adiabatic, ma'am.
Yes, here we have adiabatic, and what we have here, two systems are there, right? Here also we'll see in reversible process. We will see that in our textbook. I am showing that. I am telling about in our textbook figure. Here what we are observing here in this figure, this A is the gas be allowed expanding slowly. It will expand the process of temperature, right? So this process is reversible thermal expansion. And also here we will take that P2 and V2 and T2. What will happen here? What about P2? P2 means what here?
Pressure,
P means what? PP. Pressure. When pressure is there, we'll calculate volume and temperature also. Isn't it? Yeah.
Yes, ma'am.
Okay, next. We have in our running matter, we have thermodynamic potentials also. There we have internal energy U we will use, and F we have enthalpy, and H is the enthalpy, sorry, and F is what is F here? Helmholtz free energy, and also G is the Gibbs free energy. We will calculate it later. In next class, we will calculate all these thermodynamic potential. We will learn in that way. Okay? Yeah. Next. Come to the point of enthalpy. What is enthalpy? Anybody have? What is enthalpy? What is enthalpy? If you have any idea, this is a communication class, no? Means this when the class is running, student and teacher communication also very important.
Yes, ma'am.
I don't know, no, you are listening or you are doing some of work in your lesson.
Yeah, we are there, but we don't know this enthalpy.
Yeah, tell me, anybody have idea about this enthalpy? Yeah, tell me, you have on the screen also that slide.
Yes, ma'am. Internal energy ni volume and pressure toti measure.
You read that, no problem. You read that, whatever I written here on the screen.
Yes,
you read that. We will understand.
Finally, enthalpy is a thermodynamic potential.
Very good.
It is a state function since it is defined in terms of 3 other precisely definable state variables.
Yeah. Here what we are using here, state variables. In enthalpy, we have HUPV, no? Here,
volume and pressure.
Here, we learn that. That is thermodynamic potential, sir. Yeah. Is it correct or not?
Yes, correct. Volume and pressure.
Yes, come again. Come on, Babu, you read. You are reading only, no? Yeah.
Yeah. So, enthalpy is a measure of total energy of a thermodynamic system.
Very good. It includes the
internal energy U, which is the energy required to create a system.
Very good.
And the amount of energy required to make a room for it.
We are using here one example is a room for that enthalpy for calculation of it, right?
By displacing its environment and establishing its volume V and pressure P.
Yeah. Here H is, what is H here? Here H. Internal energy. Before slide only
H is the enthalpy, madam.
H is the enthalpy. And what about U?
Internal energy.
Yeah, U is
the internal energy.
Yeah. Internal energy. Here P is
the pressure.
V is the volume. It is show what a parallel to the first law of thermodynamics. For a constant pressure system, we will use these equations. Q is equal to delta U plus P delta V.
Since in this case, Q is equal to del H.
Yeah, H when we will calculate, we use this formula. Okay. Free energy functions. In Helmholtz free energy we have here. Where is which term we are using here? Helmholtz free energy. This is F we are using the term is. Okay. Yeah. We will define that. It is change. We are speaking about Helmholtz free energy. It is change is equal to the amount of reversible work. Again, we have to take the example of this cycle only, Carnot cycle only. There also same reversible, what we discussed before. Yeah. What will happen here? Reversible work done or a system at constant T. What is T here?
Temperature, ma'am.
Temperature, absolute temperature. We have to use that word is here in this whole Helmholtz free energy. We use that T is the absolute temperature. Are you seeing the slide?
Yes, ma'am. Slightly.
Yeah, it is a work content since it makes no reference to any quantities involved in work, such as when temperature we are taking, we can use definitely P and V. Why?
Pressure and volume.
Why?
Because it is constant, no, ma'am. Work is
Hmm. Very
temperature
good.
is constant. So
Oh, yes, you are correct. Tell me.
yeah.
When the pressure volume we use, compulsory temperature will come in this Helmholtz free energy term. Okay. And Helmholtz function is completely in general. It decreases the maximum amount of work which can be done by the system, any system, open system, closed system. You remember that these systems. Okay. Every time in every class, I will use this word system. Again, I will ask that question. What are the systems we have in journal? Okay.
Open and closed.
Open system, closed system,
Very good.
and
Isolated system?
isolated system.
Yes. These systems you have to keep in your mind. In this thermodynamics subject, we use these three systems. Completely overall, almost 80% of these systems only we used in thermodynamics. Okay. Yeah. Now come to the point, and it can increase at most by the amount of work done by on the system. Okay. So this is a Helmholtz free energy. This is introduction class. We have to know about that. What is the enthalpy? What is the Helmholtz free system? What is the Helmholtz energy? What is U? What is T? What is S? All this is the introduction class. Okay. Yeah. Next, come to the point of Gibbs free energy. This equation we will use in this Gibbs free energy. Here, what is G? G is the Gibbs free energy. That is equal to what is U? Earlier we discussed about U.
Internal energy.
Internal energy. What is T? Absolute
Absolute
temperature. What is S?
final entropy.
Final
Entropy.
entropy. And what is P?
Absolute
Absolute
pressure and
pressure.
Pressure. Absolute pressure. What is V?
volume.
Final volume.
Final volume. You all observe in this slide final enthalpy and final volume. Okay, these both we calculate in this to getting that Gibbs free equation. Okay, what is TS here? T is the absolute temperature. S is the final entropy. Okay, here what will happen in these both absolute temperature and final entropy? Energy you can get from the system environment by the heating. Whenever heat process is coming, what will happen? Absolute temperature will calculate and final entropy also will calculate in that heating system process will start. Okay. And come to
Yeah.
the point of P and V. Pressure and volume. What is volume, Mama? Can you tell anyone the definition of volume? What is volume?
Volume means the complete full area which is covered, means internal.
Hmm.
In
Inka?
that gas or heat is available.
Again, anybody? Another one?
Space occupied.
Hmm.
కూలింగ్ ఎంత వాల్యూమ్లో వెళ్తుంది అప్ అండ్ డౌన్ అనేది కూడా, అంటే నాకు చెప్పడానికి రావట్లేదు కానీ మనం
నో
హీట్
ప్రాబ్లం. నీకు ఏది ఐడియా ఉంటే అది చెప్పు. ఫ్రీ రైట్.
వాల్యూమ్ ఎలా ఉంది, ఎంత హీట్లో ఉంది, టెంపరేచర్తో మనం తెలవాలి అంటే అది ఎంత వాల్యూమ్లో ఉంది అనేసి అంటాం, కానీ దాని కరెక్ట్ ఎగ్జాక్ట్ డెఫినేషన్ తెలియదు మ్యామ్.
Yeah, I will tell that example. I will tell that what is a volume. A volume is simply defined as the amount of space occupied. Is it correct or not?
మ్యామ్ వాయిస్ కొంచెం బ్రేక్ వచ్చింది మ్యామ్.
Okay. ఇప్పుడు
ఇప్పుడు
Now
ఓకే
it's okay.
yeah. What is here exactly the volume defined as the amount of space
Space.
occupied by any three-dimension solid, isn't it? Is it correct or not?
Yeah,
Yes,
madam,
ma'am.
correct.
Yeah. So these solids can be, for example, cube, cuboid, cone, cylinder, sphere, and whatever the different spaces that is occupied in one place, right? That is in three-dimensional area. Okay, that is called the volume here.
Volume.
Okay? Yeah. What is here in this P and V? We'll take here in this equation. Work to give the system final volume will at constant pressure P will calculate. This totally will calculate the Gibbs free energy is G is equal to U minus TS plus PV. Okay, in the derivation part, everything will change. Finally, we will get the Gibbs free energy equation. Okay, yeah. Come to the point of what is the first law of thermodynamics? How many laws we have here?
Three laws.
How many laws we have in thermodynamics?
Two last,
Three
ma'am.
laws.
2 or 3?
3. Zeroth law, first law, and second law.
Very good. Zeroth law, first law,
First
and
law,
Second law.
second law, right? Yeah. Come to the point of first law. What is the first law you have on the screen? Anybody read this one? I'll tell again what
The
is the proper first law of thermodynamics.
The first law of
Are you able
thermodynamics.
to see the screen?
Yes, ma'am.
Yes, ma'am.
Yeah, you can.
The first law of thermodynamics is the application of the conservation of energy principle to heat and thermodynamics process.
Yeah, we are using here Q is equal to delta U plus A. What is here U and A? Here U
U
is
is internal energy.
Yeah, very good. Change in internal energy. We have to use that word here.
Yeah, del is
Change in internal energy. Yeah. What about Q?
Q is the
Quantity of
final.
heat.
Where heat added. Where heat added, we'll use this Q. Okay.
Quantity.
Yeah, quantity. Yes, very good. Quantity. Yeah. General word is here we use that quantity. What about A? Don't tell that area. We are using different. I have used here different word A. We'll use W here. W also we'll use here.
W అంటే వర్క్, ఏ అంటే
Yeah, here see work by the system. Here you have on the screen work by the system. Yeah.
Okay.
Come to the point of heat added. What heat added? Q is equal
quantity
to
of heat.
thermodynamic system goes to change in the internal energy and to do the work by the system. For example, we have those systems. Every time you have to learn that systems, isolated, closed system, these three systems. Okay. Yeah. So come to the first unit of our, we are entering in the unit 1. Okay. What is our unit 1?
Kinetic theory of gases.
Yes, kinetic theory of gases. That gas particles will move from one place to another. Here I am mentioning here cycle of gas particle behavior, how it was moving from one place to another place. What you are understanding here, constant motion. This is a constant motion. One particle is starting from this place. Okay, it will move from one place to
Microscopic
one place to another
place.
This is moving. Okay, and here what will happen?
It will move
When gas
continuously with the
particle
same
is
speed.
moving one place to another place, already earlier in one slide, I used this microscopic behavior. Microscopic behavior
Ma
I
ma
used here. Yeah.
Microscopic behavior means each particle of the gas.
Very good, very good. Then
Yeah.
what about microscopic properties? Generally, anybody have any idea of microscopic properties?
Again, property of the each particle.
Any idea of microscope? What will happen in microscope? Suppose I am using microscope. For example, in general word, I am using here. I am using for something, find out anything in microscope. What will happen there?
The microscopic property, I remember one thing, it has almost zero weight, or
Yeah.
we can say low.
Yeah, very good.
Which are
And
naked. We
and
can't see with
it
our
can't be
normal
seen
eyes.
the naked eye,
Very
and
good.
its volume is also negligible.
Yeah, what you are doing there when we use microscope? What we are doing there with that microscope? We are finding
Observing the particle, whatever we are placing on it, we need to observe the particle, how it is moving, or what is its behavior, or what is
yes,
happening.
very good. You are understanding this concept of particle behavior, correct?
Yes, ma'am.
Yes. And also we have here kinetic theory of gases. Some assumptions are looking here. Molecular motion and elastic collisions. Here again you have one question. What is a collision? What is collision?
Collision means when two particles or two or more particles collide, means
Here
दो particle
you see
टकराते
this
हैं.
figure.
Yeah, when they get merged with these two,
Yes.
that is called collision.
What is collision? Exact definition I want. Molecular motion means some molecule will move from one place to we will tell, anybody will tell that. What is elastic and what is elastic collision? What is elastic?
Elastic means when it is put some pressure, it will get expanded, and when we remove the pressure, it will again come to the same shape.
Yes, elastic is the property of solid material to turn to their original shape and original size. Is it correct?
Yeah, correct.
That is, we will call the elastic. What about this elastic collision?
Elastic collision means when two particles, two or more particles collide each other,
Very
the
good.
shape will again will not get deformated.
Very good.
It will come to the same shape after the collision after the collision is over.
Yes. Again, simple definition, you tell me that. What
दो
is
particle
an elastic collision?
Elastic
If we
collision.
take a slime, ma'am, two types of slime.
Very good. Yeah.
If the slime is getting together and making a one motion molecule, two slimes, two colors of slime getting together and coming in a one normal
Yes.
color. We
Yes.
can also take an example for elastic collision, ma'am.
Yes, I will give exact definition here. Here, elastic collision. Before we have to know when we are exactly entering in this chapter, we have to know about this all. Okay, that's why I am telling this. Okay, you will get one idea about this kinetic theory of gases. What is the kinetic theory of gases? Okay, yeah.
Okay.
Here, elastic collision means a collision in which there is no net loss in kinetic energy. Are you following me? A collision in which there is no net loss in kinetic energy in the system as a result of collision. Okay. Here, what is the kinetic energy, Amma? What is kinetic KE? KE is equal to
half mv square.
what is kinetic energy? What is the kinetic energy? Anybody? Babu, tell me. Bolo nama, batao. What is kinetic energy?
Kinetic energy is the energy released due to motion.
Yes.
Motion of a particle or some substance.
Okay. So, this kinetic energy is a form of energy that an object or whatever the particle has by reason of its motion. If work which transfers energy is done on the object by applying a net force, when force applying, we'll get this kinetic energy. Okay, without force it will come? Yes or
No,
no?
ma'am. No, ma'am.
Yeah,
With the
very
force
good.
only.
Yeah, and here in kinetic, come to our part. In kinetic theory of gases, we have some mathematical formations. Ideal gas law. What is ideal? Anybody have ideal gas? About ideal gas, anybody have an idea? Ideal gas? PV is equal to? PV is equal to? nRT. Very good. Then pressure volume relationship, we will see the mathematical formation and the applications of this kinetic theory of gases. So gas behavior, wherever the gas behavior we will observe here. So that is we have one application and scientific and industrial applications also we have. And also in this again assumptions of kinetic energy. So here what you are observing in this figure, large number of particles, when the large number of particles come together, what will happen? The large number of particles come together, what will happen? Large number of particles when come together, what will? ఏమవుతుందమ్మా ఎక్కువ పార్టికల్స్ ఒక చోట చేరితే ఏమవుతుంది? क्या होता है? Yeah, I will tell you that. The large number of particles when it will come together, what will happen? Suppose we are talking about the gases. So here the gas consists of a vast number of particles which allows for the statistical treatment of their behavior. Then what is the random motion? Here the random motion, the particles here, the particles are in constant or random motion colliding with each other and the walls of their container. We are using, suppose for example, container we are using. Some particles are there in that container. The random motion when it will come near together of a particle, it will happen that the walls of their containers, suppose for example, the particles will colliding each other in this random motion. కదా మనకి ఫర్ ఎగ్జాంపుల్గా స్కూల్కు వెళ్తాం. స్కూల్లో పిల్లల్ని ఒక్కసారి వదిలితే ఏమవుతుంది? ఒక క్లాస్ రూమ్లో స్కూల్లో పిల్లలు ఉన్నారు, క్లాస్లో టీచర్ లేరు. వాట్ విల్ హ్యాపెన్ దేర్?
ఫాస్ట్ గా బయటకు వచ్చేస్తున్నాం.
వన్ బై వన్ వెళ్తారా?
వెళ్ళరు మ్యామ్.
ఒకరికొకరు కొట్టుకుంటా వెళ్ళిపోతారు. దట్ రూమ్ ఈజ్ నథింగ్ బట్ అ కంటైనర్. Those students are the particles in that room. Okay. So,
Okay, ma'am.
so same thing will happen here. And here what is the negligible volume? Ante here the volume of the individual gas particles is negligible compared to the volume of this container. And again we discussed already elastic collisions and intermolar forces. When suppose intermolar, no internal molar forces means what here? there are no attractive or repulsive forces between the particles except during the collision time. Okay. So this is what today class. Next we have 25th class. Okay. Then we will continue this class, the next class. Okay na?
Okay, ma'am.
एम्मा नेक्स्ट क्लास 25th को है, ज्वाइन हो जाओ, सेम टाइम रहेगा.
Yes, ma'am.
Okay.
Okay,
Okay, ma'am.
we'll continue this class in the
Ma'am,
next
actually we have practical on Saturday, ma'am. 25th.
1 hour only, no, that is nearby lunch time, 12 to 1.
Okay, ma'am.
12 to 1 only, these days we have this class. Okay.
Okay, okay, ma'am.
Yeah.
So will be, madam, next class will be on Saturday, not Sunday.
Yeah, Saturday only 1 hour, no, that is before lunch time now, 12 to 1.
Okay, madam.
This is online class only, no, that is this is not offline class, right?
Yes,
Right.
yes, ma'am.
Whenever you are there, you start your with mobile.
Correct.
Okay,
na?
ma'am.
Yes.
Okay,
Yeah.
ma'am.
Very good, Amma. Thank you for your interaction. Okay.
Thank you so
Thank you
much,
very much,
ma'am.
ma'am.
Right, Amma. Right. Thank you.
Thank you, ma'am.
Thank you.
Yeah. We'll meet next time, next class.
Okay, ma'am.